You see, there's something that's been bothering me for years. Something that most people don't think about. We're told that in 1969, humans landed on the moon. Neil Armstrong took that famous first step. Buzz Aldrin followed. The whole world watched on television. It's one of the defining moments of human history. But here's the thing. When you actually look at the physics, when you calculate the energies involved, when you analyze the technology they had available, when you consider the radiation, the temperatures, the computational power, you start to ask yourself a very uncomfortable question. How did they actually pull this off? Now, before you think I'm some conspiracy theorist, let me be clear. I'm a physicist. I work on string theory at the City University of New York. I believe in evidence. I believe in mathematics. I believe in the scientific method. And that's exactly why this question fascinates me. Because when you do the math, when you look at the engineering challenges, the moon landing seems almost impossible. Think about it. In 1969, the most powerful computer available to NASA had less computing power than your smartphone. In fact, the Apollo guidance computer had 64 kilobytes of memory. 64 kilobytes. Your smartphone has millions of times more memory than that. The entire Apollo program was navigated with less computational power than a modern calculator. And yet somehow they calculated trajectories to the moon with pinpoint accuracy. They navigated through space. They landed on the lunar surface. They took off again. They rendezvoused with the command module in orbit. They came back to Earth. All with a computer less powerful than the chip in your car key. Now, how is that possible? Well, let me explain something about orbital mechanics. When you're trying to get to the moon, you're not just pointing a rocket and firing. You're dealing with what we call the three-body problem. You have the Earth, you have the moon, and you have your spacecraft. Each one is pulling on the others with gravity. And the mathematics of the three-body problem are notoriously difficult. In fact, there's no exact solution to the three-body problem. You can't write down a simple equation that tells you exactly where everything will be at any given time. You have to use approximations. You have to use numerical methods. You have to run complex calculations again and again. And in 1969, they did this with 64 kilobytes of memory. Think about that for a moment. Modern scientists with supercomputers millions of times more powerful still struggle with orbital mechanics. We use massive computational resources to calculate satellite trajectories. And yet NASA, with 1960 seconds technology, nailed it on the first try. Well, actually not the first try. There were the Apollo 8, 9, and 10 missions that tested various components, but still the margin for error was incredibly small, and they succeeded every single time after Apollo 13's famous accident. They brought the astronauts home safely. So, the question isn't whether the moon landings happened. The question is how. How did they overcome challenges that seem almost insurmountable? Let me give you another example. Radiation. Space is filled with radiation. Cosmic rays, solar wind, radiation trapped in the Earth's magnetosphere. When you leave Earth's protective magnetic field, you're exposed to enormous amounts of radiation. Now, the Apollo spacecraft had aluminum walls. Aluminum, that's it. The command module was essentially a thin aluminum can, and the astronauts spent days in space traveling to the moon, and back protected only by this thin metal shell. Let me tell you something about radiation shielding. To effectively block high-energy cosmic rays, you need thick shielding. Lead concrete, water-dense materials that can absorb the radiation. A few millimeters of aluminum. That's not going to do much against cosmic rays. And then there's the Van Allen radiation belts. These are zones of intense radiation surrounding Earth. Discovered by James Van Allen in 1958, the belts contain high-energy protons and electrons trapped by Earth's magnetic field. And to get to the moon, you have to pass through them. Now, NASA says the astronauts passed through the Van Allen belts quickly, spending only about an hour in the most intense regions, and that the radiation dose was manageable. And you know what? The math actually supports this. If you calculate the radiation exposure for a fast transit through the belts, it comes out to something humans can survive. But here's what's interesting. In 2014, NASA released a video where one of their engineers said that we need to solve the radiation problem before we can send humans beyond low Earth orbit. He said, and I quote, "Why must solve these challenges before we send people through this region of space?" Wait a minute. We must solve these challenges, but we already sent people through this region of space 12 times in the Apollo program. So, what's he talking about? Well, the answer is complicated. Modern safety standards are much stricter than they were in the 1960 seconds. Today, we want to minimize radiation exposure as much as possible. In the 1960 seconds, they were willing to accept higher risks. The astronauts knew they were being exposed to radiation. They accepted it. It was part of the job. But still, it raises an interesting question. If we did it in 1969 with primitive technology, why is it so hard now? Why are we acting like it's some unsolved problem? Let me tell you another thing that bothers me. The temperatures on the moon. During the lunar day, which lasts about 2 weeks, temperatures on the surface reach 127 degrees C. That's 260 degrees Fahrenheit, hot enough to boil water. And during the lunar night, temperatures drop to minus 173 degrees C. That's minus 280 F, cold enough to freeze carbon dioxide. Now, the Apollo astronauts landed during the lunar morning when temperatures were relatively moderate, but still they were dealing with extreme heat. The lunar surface was baking in direct sunlight. No atmosphere to diffuse the heat, no clouds to provide shade, just raw, intense solar radiation. And their space suits, they had a cooling system. Yes, water-cooled garments worn under the suit. But think about the engineering challenge. You're designing a suit that has to keep a human comfortable in extreme heat while also being flexible enough to allow movement, strong enough to maintain pressure, and light enough to be practical. And they pulled it off. The suits worked. The astronauts didn't overheat. They didn't freeze. They worked on the lunar surface for hours at a time. It's remarkable. Almost too remarkable. Now, let me talk about something else. The lunar module. This was the spacecraft that actually landed on the moon. And when you look at it, it's not impressive. It looks like it was built in someone's garage. Thin metal walls, foil-like covering, spindly legs. It looks fragile. It looks primitive. And yet, this thing had to descend from lunar orbit, land on an unknown surface, then take off again, and rendezvous us with a command module. All with a rocket engine that had never been tested in lunar conditions. All controlled by astronauts using manual controls and that primitive computer. Think about what's involved in landing on the moon. You're descending in 1/6 gravity. Your engine is firing to slow you down. You're trying to find a safe landing spot. You have limited fuel. If you run out before you land, you crash. If you land too hard, you crash. If you land on a slope, you tip over. And they did this 6 times successfully. Every single time. Armstrong had to manually fly the Eagle to avoid a boulder field. He landed with less than 30 seconds of fuel remaining. 30 seconds. That's how close they came to disaster. And the other missions, they all landed safely. No crashes, no disasters. Every landing was successful. Now, that's either incredible skill and luck or something else is going on. Let me give you another example. The photographs. The Apollo astronauts took thousands of photographs on the moon. Beautiful, clear, perfectly exposed photographs. And they did this with film cameras, Hasselblad cameras modified for lunar conditions. Now, think about what's involved in photography. You need the right exposure. Too much light, the image is washed out. Too little light, it's too dark. You need the right focus. You need to hold the camera steady. And the astronauts were doing this while wearing bulky spacesuits with thick gloves. They couldn't look through a viewfinder. They had cameras mounted on their chests. They were essentially shooting blind. And yet almost every photograph is perfectly framed, perfectly exposed, perfectly focused. How professional photographers working in comfortable conditions with modern equipment would struggle to achieve that success rate. And yet astronauts in bulky suits on the moon nailed it almost every time. Now NASA's answer is that they trained extensively. They practiced for months. They knew exactly how to set the camera for lunar conditions. And okay, that makes sense. But still the success rate is remarkable. And then there's the film itself. Photographic film is sensitive to radiation. Cosmic rays can fog film, create artifacts, ruin images, and yet the Apollo film survived. The images are clear, no significant radiation damage. How did they protect the film? How do they ensure it wouldn't be ruined by the intense radiation of space? These are the questions that keep me up at night. Not because I think the moon landings were faked, but because I want to understand how they actually did it, how they overcame challenges that seem almost insurmountable. You see, when I was 8 years old, I saw the Apollo missions on television. I watched Armstrong step onto the moon and I was inspired. I thought if we can do that, we can do anything. It sparked my interest in science. It made me want to become a physicist. And now, decades later, as I understand more about the physics, the engineering, the challenges involved, I'm even more impressed because what they accomplished was extraordinary, almost miraculous. But here's what really gets me. We haven't been back. It's been over 50 years since the last moon landing. We've sent robots to Mars. We've built the International Space Station. We've launched telescopes that can see to the edge of the universe. But we haven't sent humans back to the moon. Why not? If we did it in 1969 with primitive technology, it should be easy now, right? We have better computers, better materials, better rockets. So why haven't we gone back? The official answer is money. It's expensive. There's no pressing need. We can do most science with robots. And okay, those are all valid points. But still, you think that in 50 years someone would have wanted to go back? China, Russia, Europe, private companies, someone would have done it by now. Unless it's harder than we think, unless the challenges are greater than we realized, unless there's something about the moon landings that we don't fully understand. Now, let me talk about the rocket equation. This is fundamental to space travel. It's called the Tsiolkovsky rocket equation after the Russian scientist who first formulated it. And it tells you how much fuel you need to reach a certain velocity. The problem is it's exponential. If you want to go faster, you don't just need more fuel. You need exponentially more fuel. And that fuel has mass. So you need more fuel to lift the fuel. It's a vicious cycle. To escape Earth's gravity, you need to reach about 11 kilometers per second. That's 25,000 miles per hour. And to do that, you need a rocket that's mostly fuel. The Saturn V rocket that launched the Apollo missions was 85% fuel by mass. Only 15% was the actual spacecraft and payload. And they did this in the 960 seconds. They built the most powerful rocket ever made. 3,000 tons of thrust, and it worked. Every single time it launched, it worked. No catastrophic failures, no explosions on the launch pad. Now, compare that to today. We're still struggling to build reliable heavy lift rockets. SpaceX's Starship has had multiple test failures. NASA's Space Launch System is years behind schedule and billions over budget. And yet in the 960 seconds, they built the Saturn V and it worked on the first try. How did they achieve that level of reliability with 960 seconds technology with slide rules instead of computers, with less advanced materials, with less experience? The answer, according to NASA, is that they had unlimited resources. The Apollo program cost over $25 billion in 962 seconds money. That's over $150 billion in today's dollars. They had the best engineers, the best facilities, the full support of the government, and they were motivated by the Cold War. They had to beat the Soviets to the moon. And okay, that makes sense. When you throw enough money and talent at a problem, you can solve it. But still, the engineering achievement is staggering. They essentially invented the technology as they went along. Fuel cells, life support systems, space suits, lunar rovers, all of it was brand new, and it all worked. Let me tell you about another challenge: communication. The moon is about 2.40 thousand miles from Earth. Radio signals travel at the speed of light, which means there's about a 1.3-second delay each way. So, when Mission Control talked to the astronauts, there was a 2.6-second round-trip delay. Now, that doesn't sound like much, but think about landing on the moon. You're descending. You're looking for a landing spot. Mission Control is monitoring your fuel, your altitude, your velocity, and there's a 2.6-second delay in all communications. If something goes wrong, Mission Control can't help you in real time. By the time they see the problem and send a command, it's too late. The astronauts have to make split-second decisions on their own. And they did. Armstrong manually flew the lunar module to avoid a boulder field. He had seconds to make that decision, no time to consult with Mission Control. He just did it and it worked. That takes incredible skill, incredible training, incredible courage. And the fact that it worked is testament to the quality of the astronauts and the mission planners. But it also raises a question. How many things could have gone wrong? How many potential failures were there, and how do they avoid all of them? You see, space travel is unforgiving. There's no margin for error. A tiny leak in a spacesuit means death. A malfunction in the life support system means death. A problem with the rocket engine means death. Everything has to work perfectly every single time. And in the Apollo program, with a few exceptions like Apollo 13, everything did work. The odds of that are remarkably small. It's like flipping a coin 100 times and getting heads every single time. Possible? Yes, but unlikely. Now, I'm not saying it didn't happen. I'm saying it's remarkable that it did happen. The engineering, the planning, the execution, all of it had to be perfect, and it was. Let me talk about something else that fascinates me. The flag. You've all seen the images. The American flag planted on the lunar surface. And in some of the footage, the flag appears to be waving, moving in the wind. But wait, there's no atmosphere on the moon, no air, no wind. So how can the flag be waving? Now, skeptics jump on this and say, aha, proof that it was filmed on Earth. But the explanation is actually simple. The flag had a horizontal rod at the top to keep it extended. And when the astronauts planted the pole, they twisted it back and forth to drive it into the ground. That twisting motion made the flag wave. And in the vacuum of the moon, with no air resistance, the flag kept moving for a while. It's physics. Simple physics. But it looks weird because we're not used to seeing flags in a vacuum. On Earth, a flag would stop moving almost immediately because air resistance would damp the motion. But on the moon, the flag keeps oscillating. So, the waving flag isn't evidence of a hoax. It's evidence that they really were in a vacuum. It's evidence that they really were on the moon. But here's what's interesting. The fact that people question this shows how counterintuitive space is, how different it is from our everyday experience. And that's exactly why the moon landings seem impossible, because they required mastering an environment completely unlike anything on Earth. Now, let me talk about the rocks. The Apollo missions brought back 842 pounds of lunar rocks and soil. These samples have been studied by scientists all over the world for over 50 years. And they're genuine. They're unlike any rocks on Earth. Lunar rocks have certain characteristics. They contain minerals that form only in the absence of water. They have tiny impact craters from micrometeorites. They have no signs of weathering because there's no weather on the moon. And they're old, really old, over 4 billion years old in some cases. Now, could these rocks have been faked? Could they have been manufactured in a laboratory? No, Not with 1960 seconds technology, not with today's technology. We can create rocks with these characteristics. The isotope ratios, the mineral compositions, the age, all of it matches what we'd expect from the moon. So, the rocks are real. They came from the moon. And the only way to get them was to go there and bring them back. But here's what's interesting. The Soviet Union also brought back lunar rocks using unmanned probes. The lunar program successfully returned samples from the moon 3 times, much smaller amounts than Apollo, but still they did it robotically. So it was possible to get lunar rocks without sending humans. Does that prove Apollo was faked? No. Because the Soviet Union, our greatest rival, confirmed that Apollo happened, they tracked the missions. They monitored the communications. They had every incentive to expose a hoax if it existed. And they didn't. They acknowledged that America won the space race. That's pretty strong evidence right there. If your biggest enemy, the one you're competing against, says you won, then you probably won. Now, let me talk about radiation again, because this is really important. A lot of people focus on the Van Allen belts, but there's another source of radiation in space, solar particle events. These are bursts of high-energy particles from the sunday. They're unpredictable. They can happen at any time, and they're dangerous. If astronauts are caught in a solar particle event outside Earth's magnetosphere, they could receive a lethal dose of radiation. It's one of the biggest dangers of deep space travel. Now, during the Apollo program, there were no major solar particle events during the missions. The astronauts were lucky. If there had been a big solar storm, they could have been in serious trouble. But NASA monitored solar activity carefully. They had forecasts. They knew when it was safe to launch and when it wasn't. And they got lucky. The timing worked out. But think about that. They were gambling with the astronauts' lives. If a solar storm had erupted while they were on the moon, there would have been nothing they could do. The lunar module didn't have enough shielding to protect them. They would have been exposed. That's the kind of risk they were willing to take in 1969, and it worked out. But it easily could have gone the other way. So when I look at all of this, the technology, the challenges, the risks, I'm amazed that it worked. I'm amazed that we actually pulled it off. It really was an incredible achievement. But that's also why it's so hard to do again, because we understand the risks better now. We're not willing to accept the same level of danger. We want better shielding, better life support, better redundancy, and all of that makes it more expensive and more complicated. In the 960 seconds, they just went for it. They accepted the risks. They pushed forward and they succeeded. Now, let me tell you something personal. When I built my particle accelerator in high school, people thought I was crazy. They said, "You can't do that. You don't have the resources. You don't have the knowledge." But I did it anyway. I went to junkyards and bought parts. I wound coils of copper wire. I figured it out. And that's what NASA did with Apollo. They had a seemingly impossible goal, and they figured it out. They innovated, they improvised, they made it work. That's the American spirit. That's what we're capable of when we're motivated, when we have a clear goal and the will to achieve it. But it also shows how rare that kind of achievement is, how everything has to align. The technology, the resources, the political will, the luck, all of it has to come together at the right moment. And in 1969, it did. We went to the moon. We achieved the impossible. But here's the question I really want to explore. If we did it once, why is it so hard to do it again? What changed? What did we lose? And what does that tell us about the challenge of space exploration? Because if going to the moon was impossible with 962 seconds technology and is still hard with modern technology, then maybe space is more hostile, more challenging, more dangerous than we like to admit. Maybe the moon landings weren't just an engineering achievement. Maybe they were a miracle, a perfect storm of talent, resources, timing, and luck that came together once and might never come together again. Or maybe, and this is what I believe, maybe they showed us what we're capable of. Maybe they proved that humans can do the impossible when we set our minds to it. And maybe that's the real lesson. Not that it's impossible, but that it requires everything we have. And that brings me to the end of part 1. We've looked at the challenges, the radiation, the temperatures, the technology, the risks. We've seen how unlikely success was, and yet it happened. In part 2, we're going to dig deeper. We're going to look at the specific technologies that made it possible. The rocket engines, the navigation systems, the life support. We're going to understand exactly how they overcame each challenge, and we're going to explore why, despite all our modern advantages, we still haven't gone back. So, we've established that the moon landings faced extraordinary challenges. Now, the next question is, and this is where things get really interesting, how exactly did they solve these problems? What specific technologies did they use? And why can't we easily replicate them today? You see, when you dig into the engineering details of the Apollo program, you find solutions that seem almost too clever, too perfectly designed. It's like they knew exactly what would work before they even tested it. And that's what fascinates me as a physicist. How did they get it right? Let me start with the most critical component, the rocket engine. Specifically, the F1 engine that powered the first stage of the Saturn V. This engine produced 1.5 million pounds of thrust. It burned 3,000 LEVs of fuel per second. 3,000 lb every single second. That's more than a small car. And here's what's remarkable. They designed this engine in the early 90-60 seconds. They didn't have computer simulations. They didn't have advanced material science. They used slide rules and wind tunnels and physical testing. And yet, they created the most powerful single-chamber rocket engine ever built. Even today, with all our computational power, we struggle to match the F1. SpaceX's Raptor engines are impressive, but they produce about half the thrust of an F1, and the F1 was built 60 years ago. So, how did they do it? Well, let me tell you about the development process. They tested the F1 thousands of times. They blew up dozens of engines. They had catastrophic failures. Engines exploding on the test stand, but they kept iterating, kept improving until they got it right. And when they finally got it right, it worked. 13 Saturn V launches, 13 successes, no failures. Every single F1 engine performed exactly as designed. Now think about the complexity here. Each F1 engine had thousands of parts. Pumps, valves, injectors, chambers. All of it had to work in perfect synchronization. The fuel and oxidizer had to mix at exactly the right ratio. The combustion had to be stable. The cooling had to prevent the engine from melting. And they achieved this with 960 seconds manufacturing techniques. No computer control machining, no advanced quality control systems, just skilled machinists and engineers doing everything by hand. It's extraordinary, almost unbelievable. But the engines exist. You can see them in museums. You can examine them. They're real. But here's what's interesting. NASA lost the detailed manufacturing specifications for the F1. Not the basic designs, those exist, but the specific techniques, the tricks the machinists used, the subtle adjustments they made. A lot of that knowledge was lost when the program ended and the engineers retired. So even though we have F1 engines, even though we can study them, we can't easily build new ones. We'd have to reverse engineer them. Figure out how they were made. And that's harder than you might think. This is what engineers call tacit knowledge. Knowledge that exists in people's hands and minds, not in blueprints and documents. And when those people retire or die, the knowledge goes with them. So, in a very real sense, we've lost the ability to go to the moon the way we did in the 9-60 seconds. Not because the physics changed, not because it's impossible, but because we lost the institutional knowledge, the manufacturing techniques, the entire industrial infrastructure that made it possible. Now, let me talk about the guidance computer. The Apollo Guidance Computer, or AGC, this was the computer that navigated the spacecraft to the moon. And as I mentioned earlier, it had 64 kilobytes of memory. That's nothing. Absolutely nothing by today's standards. But here's what's remarkable. The software was perfect or nearly perfect. It had to be because there was no way to update it in flight. No patches, no bug fixes. Whatever code they loaded before launch, that's what they were stuck with. And the programmers achieved this. They wrote code so efficient, so carefully optimized that it fit in 64K and did everything needed: navigation, guidance, control, displays, everything. Margaret Hamilton led the software team. She pioneered many of the concepts we now take for granted in software engineering. Error checking, priority scheduling, robust fault tolerance, all of it was invented for Apollo, and the code worked. During the Apollo 11 landing, the computer was overloaded. It was trying to process too much data. Alarms were going off, but the software handled it. It prioritized the critical tasks. It kept running and Armstrong landed safely. That's incredible software engineering. Even today, with all our tools and techniques, creating software that's reliable is difficult. And they did it in the 960 seconds with primitive tools. But here's what I find fascinating. Modern spacecraft computers are much more powerful, much more sophisticated, but they're also more complex, more prone to bugs, more vulnerable to failures. The Apollo guidance computer was simple. It did one thing, and it did it perfectly. Modern computers try to do everything, and sometimes complexity is the enemy of reliability. So in some ways we've gone backwards. We have more powerful computers, but less reliable ones. We have more features but more bugs. We've traded simplicity for capability. And that's one reason why it's hard to go back to the moon, because we can't accept the simplicity of the Apollo approach. We want more capability, more redundancy, more safety features, and all of that adds complexity. Now let me talk about the space suits. The Apollo A-70L spacesuit was a marvel of engineering. It had to maintain pressure about 3.7 pounds per square inch. It had to provide oxygen. It had to remove carbon dioxide. It had to regulate temperature. And it had to be flexible enough to allow the astronauts to move. Think about what's involved here. The pressure inside the suit wants to make it balloon out like an inflated tire. But the astronauts needed to bend their joints, move their fingers, walk around. So the suit had to have special joints, convoluted sections that allowed movement while maintaining pressure. And the cooling system was ingenious. Water-cooled garments worn under the suit. Water circulated through tubes absorbing body heat, then passing through a sublimator that vented the heat into space. Elegant, simple, effective. But here's what's remarkable. They designed these suits in just a few years. They tested them, refined them, and they worked. The astronauts spent hours on the lunar surface in these suits. No failures, no catastrophic leaks, no overheating. Compare that to today. NASA's new space suit program has been in development for over a decade and is billions over budget. The suits still aren't ready, and when they are ready, they'll be more complex, more capable, but also heavier and more expensive than the Apollo suits. Why? Because we've added requirements. We want longer mission duration. We want better mobility. We want more sizes to fit different body types. All good things, but all of them add complexity and cost. The Apollo suits were custom-made for each astronaut. They fit perfectly, but they were also specialized for moon missions. They wouldn't work as well for Mars or for long-duration spacewalks. So again, we're trading simplicity for versatility, and that makes it harder and more expensive. Now, let me talk about something that really puzzles people. The lunar module. This thing looked like it was made from tin foil and curtain rods. It didn't look like it could fly in Earth's atmosphere, let alone land on the moon. But appearances are deceiving. The lunar module was actually a brilliant piece of engineering. You see, on the moon there's no atmosphere, no aerodynamics. So, the spacecraft doesn't need to be streamlined, it just needs to be functional. And the thin walls, that's because every pound matters. Getting mass to the moon is incredibly expensive in terms of fuel. So, they made everything as light as possible. The walls were just thick enough to maintain pressure and provide micrometeorite protection, nothing more. And you know what? It worked. The lunar module landed 6 times. It took off 6 times. It rendezvoused with the command module 6 times. Perfect record. But here's what's interesting. The descent engine, the rocket that lowered the lunar module to the moon's surface, had never been tested in a full landing profile before Apollo 11. They tested it on Earth in vacuum chambers, in simulators, but never in actual lunar conditions. So when Armstrong and Aldrin descended to the moon, they were essentially test pilots. They were trying something that had never been done before, and it worked on the first attempt. Now, you might say they were lucky, and maybe they were, but I think it's more than luck. I think it's a testament to the quality of the engineering, the thoroughness of the testing, the skill of the astronauts, but it also shows how much risk they were willing to accept. Today, we would never attempt something like that. We'd want multiple unmanned test landings first. We'd want to prove the system before we put humans on it. And that's another reason why it's hard to go back, because our risk tolerance has changed. We're not willing to accept the same level of danger that they accepted in the 9 to 60 seconds. Now, let me talk about navigation. How do they know where they were? How do they navigate from Earth to the moon with such precision? Well, they use several techniques. First, they had powerful telescopes on Earth tracking the spacecraft. Ground stations could measure the spacecraft's position and velocity by analyzing the radio signals, but they also had onboard navigation. The spacecraft had a sextant. Yes, a sextant like sailors used for centuries, adapted for space. The astronauts could sight on stars and use those measurements to calculate their position. And the guidance computer would take all this information, the ground tracking, the sextant measurements, the inertial measurements, and compute the optimal trajectory. It's remarkable when you think about it. They were navigating across 250,000 miles of space with a combination of ancient techniques, the sextant, and cutting-edge technology. And it worked. But here's what fascinates me. The accuracy was extraordinary. They could hit a target on the moon within a few miles. That's like throwing a dart from New York and hitting a bullseye in Los Angeles. The precision required is mind-boggling. And they did it with 960 seconds technology with limited computational power, with techniques that seem almost primitive by today's standards. Today we have GPS, we have precise atomic clocks, we have powerful computers. Navigation should be easier, and in some ways it is. But in other ways we become dependent on these systems. We've lost the ability to navigate using simpler methods. And that's a problem for deep space missions. GPS only works near Earth. Our atomic clocks need to be synchronized with Earth-based systems. If something goes wrong, if we lose contact with Earth, can we still navigate? The Apollo astronauts they had backup methods. They could navigate by the stars if necessary. That robustness is something we need to recapture. Now, let me talk about life support. Keeping astronauts alive in space is incredibly challenging. You need oxygen. You need to remove carbon dioxide. You need water. You need temperature control. You need waste management. The Apollo spacecraft used chemical systems for most of this. Oxygen was stored in tanks. Carbon dioxide was removed using lithium hydroxide canisters. Water was a byproduct of the fuel cells that generated electricity. It was a consumable system. Use it once and throw it away. Not very efficient, but simple and reliable. Today, the International Space Station uses regenerative systems. It recycles water. It splits water into oxygen and hydrogen. It scrubs and recycles the air. Much more efficient for long duration missions, but also much more complex. More things to break, more maintenance required. For a moon mission, the Apollo approach was perfect. The missions were short, just a week or so. Consumables worked fine. But for Mars, for longer missions, we need regenerative systems. We can't carry enough consumables for a multi-year mission. So, we're developing these systems, testing them on the ISS, but they add complexity, they add mass, they add cost. And that's another reason why going back to the moon is harder, because we're not just trying to replicate Apollo. We're trying to build systems that will work for longer, more ambitious missions. Now, let me address something that conspiracy theorists love to bring up: the photographic evidence. They say the photos are too perfect, too well composed, too professional. And you know what? They're right about one thing. The photos are remarkably good. Almost every shot is well framed and properly exposed. But here's the explanation. The cameras were specially modified Hasselblad 500 EL cameras. They had an RAO plate, a glass plate with crosshairs etched on it that imprinted a grid on every image. This grid serves two purposes. One, it proves the photos are unaltered. Any editing would distort the grid. Two, it allows scientists to measure distances and sizes in the photos. The cameras had fixed focus set to the hyperfocal distance. So everything from about 10 fF to infinity was in focus. The astronauts didn't have to focus. They just had to point and shoot. The exposure was preset based on the lighting conditions on the moon, the sun, the lunar surface reflectance. It's all very predictable. So they could set the exposure in advance and it would work for almost every shot. And the composition the astronauts practiced. They took thousands of practice photos on Earth. They trained until framing a shot became second nature. So the quality of the photos isn't evidence of a hoax. It's evidence of careful preparation and good engineering. But here's what's interesting. We have the original film, the negatives, and they show evidence of being exposed in space. Tiny tracks from cosmic ray hits. These are high-energy particles that pass through the film and leave traces. You can see them if you look carefully. These cosmic ray tracks are impossible to fake. You can't create them in a lab, at least not convincingly. They're proof that the film was exposed to the radiation environment of space. So, the photos are real. They were taken on the moon and the quality is due to good preparation, not fakery. Now, let me talk about something that's often overlooked: the logistics, the sheer scale of the Apollo program. At its peak, 400,000 people were working on Apollo. Contractors, engineers, technicians, administrators across the entire United States. If the moon landings were faked, all those people would have to be in on the conspiracy. Or at least a large number of them would have to know. And in 50 years, not one person has come forward with credible evidence of a hoax. Think about that. Humans are terrible at keeping secrets, especially big secrets involving lots of people. Someone always talks. Someone always leaks. And yet, despite thousands of people working on Apollo, despite 50 years of investigation by skeptics and conspiracy theorists, no one has produced any credible evidence of a hoax. The simplest explanation: it wasn't a hoax. It really happened. But let me address another common claim: the flag waving. I mentioned this earlier, but let me go deeper. In the vacuum of the moon, objects behave differently than on Earth. There's no air resistance. So, when you set something in motion, it keeps moving. It oscillates longer. It takes longer to settle. The flag had a horizontal rod at the top to keep it extended. When the astronauts planted the flagpole, they had to twist it and push it into the lunar soil. That twisting created motion in the flag, and because there's no air resistance, the flag kept waving for several seconds. In some of the video footage, you can see the flag moving. But if you watch carefully, you'll notice it only moves when the astronauts are handling the pole. When they step away, the flag continues to move briefly, then stops. Exactly as you'd expect in a vacuum. On Earth, in air, the flag would stop moving almost immediately. The air resistance would damp the oscillations. But on the moon, the flag keeps moving. That's actually evidence that they were in a vacuum. Evidence that they were really on the moon. Now, let me talk about the shadows. Another common conspiracy claim is that the shadows in the lunar photos go in different directions, which they say proves multiple light sources, which they say proves studio lighting. But the explanation is simple geometry. The moon's surface isn't flat, it's uneven. There are hills, craters, slopes. When light hits an uneven surface, shadows can appear to go in different directions, even though there's only one light source, the sunday. You can test this yourself. Go outside on a sunny day. Look at the shadows on uneven ground. They don't all point in exactly the same direction. That's normal. That's how light and shadows work. So, the varying shadows aren't evidence of multiple light sources. They're evidence of an uneven surface, which is exactly what the moon has. Now, let me talk about something really important: the tracking data. During the Apollo missions, radio telescopes around the world tracked the spacecraft. Amateur radio enthusiasts picked up the signals. The Soviet Union monitored everything. These independent observers all confirmed that the signals were coming from the moon. They could tell by the time delay radio signals travel at the speed of light. So there's a 1.3-second delay from the moon. They could tell by the Doppler shift in the signals as the spacecraft moved. You can't fake that. You can't create signals that appear to come from the moon when they're actually coming from Earth. The physics doesn't allow it. So we have independent verification from multiple sources that the Apollo spacecraft went to the moon. Not just NASA saying it, independent observers confirming it. That's pretty strong evidence. Now let me talk about the retroreflectors. During the Apollo missions, astronauts place laser retroreflectors on the lunar surface. These are special mirrors that reflect light back exactly in the direction it came from. And you know what? You can bounce a laser off these retroreflectors right now. Observatories around the world do it regularly. They measure the distance to the moon with incredible precision by timing how long it takes light to travel to the retroreflector and back. How did those retroreflectors get there? Someone had to place them. And the only missions that went to those locations were the Apollo missions. So, we have physical evidence still on the moon, still functional after 50 years, proving that astronauts were there. Now, conspiracy theorists say that unmanned probes could have placed the retroreflectors. And technically, that's true. The Soviet Union did place retroreflectors on the moon using unmanned missions. But if Apollo was fake, why would NASA bother sending unmanned missions to place retroreflectors? That would be almost as hard as sending astronauts. What's the point? The simplest explanation is that astronauts placed them because astronauts went to the moon. Now, let me talk about something that really demonstrates the challenge. The Saturn V rocket. This thing was massive, 363 feet tall, 6.5 million pounds, fully fueled. The largest, most powerful rocket ever built. And it worked. 13 launches, 13 successes, including launching humans to the moon 6 times. But here's what's interesting. We can't build a Saturn V today. Not because we don't have the technology, but because we don't have the infrastructure. The factories that build the components have closed. The tooling has been scrapped. The supply chains have disappeared. We could design a new heavy lift rocket, and we are with the Space Launch System, but it would be different from the Saturn V. It would use different engines, different materials, different techniques. So in a very real sense, the Saturn V is a lost capability. We did something in the 960 seconds that we can't easily repeat today. Not because it's impossible, but because we'd have to rebuild an entire industrial infrastructure. And that's expensive, really expensive, which is why we haven't done it. But this also proves that the Saturn V was real, that it flew, that it worked, because we have the hardware, we have the launch pads, we have the documentation, we have the photos and videos of the launches. All of that exists. It's not a hoax. It's history. Now, let me talk about Apollo 13. This is actually one of the strongest pieces of evidence that the moon landings were real. Because if you're faking missions, why would you fake a failure? Apollo 13 suffered an explosion in the oxygen tanks. The mission had to be aborted. The astronauts barely made it home alive. It was a near disaster that could have been a tragedy. If NASA was faking the missions, they would have faked a success, not a failure. They wouldn't have risked the negative publicity, the questions, the investigations. But Apollo 13 really happened. The explosion was real, the emergency was real, and the successful return of the astronauts was real. And you know what? The way they solved the problem demonstrates the reality of spaceflight. They had to improvise. They had to use duct tape and cardboard to adapt the air scrubbers. They had to conserve power. They had to manually navigate using the stars and the Earth's horizon. All of those problems and the solutions are completely consistent with real space flight. They're the kinds of challenges you'd face in space. And the solutions are the kinds of clever improvisations that real engineers and astronauts would come up with. You can't fake that level of detail. You can't script those kinds of realistic problems and solutions. They had to be real. So Apollo 13 actually proves that the moon missions were real because a hoax wouldn't include a near-fatal failure. Now, let me address the radiation question one more time because it's really important. A lot of people focus on the Van Allen belts, but the Apollo spacecraft passed through the belts quickly in about an hour, and they passed through the thinner regions of the belts, not the most intense parts. The total radiation dose the astronauts received from the Van Allen belts was relatively small. Estimates range from 1 to 10 rem depending on the mission. That's comparable to a few years of natural background radiation on Earth. Not safe, certainly not something you'd want to do repeatedly, but survivable. And in fact, the astronauts did survive. They didn't suffer radiation sickness. They didn't die young from cancer at higher rates than the general population. So, the radiation was a risk, but it was a manageable risk, and they managed it. But here's what's interesting. Modern spacecraft would use different trajectories. They'd spend less time in the belts. They'd use better shielding. They'd have better radiation monitoring. Not because it's impossible to transit the Van Allen belts, but because we can do it safer now. We don't have to accept the same level of risk. And that's another reason why it's harder to go back, because we're not willing to cut corners the way they did in the 960 seconds. Now, let me talk about the lunar samples. 842 libs of rocks and soil. These samples have been studied by scientists all over the world. Thousands of scientific papers have been published based on these samples. And the samples tell a consistent story. They're from the moon. They formed in the absence of water and atmosphere. They're ancient, billions of years old. They've been bombarded by micrometeorites and solar wind. All of this is exactly what we'd expect from the moon. And it's impossible to fake. We don't have the technology to create fake lunar rocks that would fool every scientist who studied them for 50 years. So, the rocks are real. They came from the moon. And the only way to get them was to go there. But here's what really convinces me. The samples from different Apollo missions are different. The rocks from the highlands are different from the rocks from the Maria. The soil composition varies from site to site. If you were faking samples, you'd probably make them all similar. But the real samples show the geological diversity of the moon. Different regions have different compositions, different ages, different histories. That level of detail is impossible to fake You'd have to know in advance what each region of the moon was like. And we didn't know that before Apollo. We learned it from Apollo. So the diversity of the samples proves they're real. And that proves the missions were real. Now, let me talk about something that really demonstrates the impossibility and the possibility of the moon landings. The timing. President Kennedy announced the moon goal in 1961. We landed on the moon in 1969, 8 years. We went from barely able to put a man in orbit to landing on the moon in 8 years. Think about that. In 1961, the United States had put exactly one person in space, Alan Shepard, for 15 minutes. We never done a spacewalk. We never docked 2 spacecraft. We never spent more than a day in space. And 8 years later, we landed on the moon. That's an incredibly short time frame. It seems impossible. And in many ways, it was impossible. They had to invent almost everything from scratch. But they did it. How? Unlimited resources, political will, the best minds in the country, and a deadline. That deadline was crucial. Kennedy said we'd do it before the end of the decade. That gave them a concrete goal, a ticking clock, and nothing motivates like a deadline. Today, we don't have that. We have ambitious goals, but no hard deadlines, no national commitment, no sense of urgency. And that's why it's taking so long to go back. Not because it's harder technologically, but because we don't have the same focus, the same resources, the same political will. So, in the end, when I look at all the evidence, the engineering, the physics, the documentation, the independent verification, I'm convinced the moon landings happened. They were real, but I'm also amazed because they really were impossible, or they should have been. The challenges were enormous. The risks were extreme. The technology was primitive, and yet they succeeded through brilliant engineering, meticulous planning, incredible skill, and, yes, some luck. They achieved the impossible. And that brings me to part 3, where we're going to explore the biggest question of all. If we did it once, why haven't we done it again? What does that tell us about space exploration, about human ambition, about our future? And what would it take to not just go back to the moon, but to go beyond to Mars, to the outer solar system, to the stars? So, we've arrived at this profound question. We went to the moon. We proved it was possible. We achieved one of the greatest technological feats in human history. And then we stopped. We haven't been back in over 50 years. Why? You see, this is what really bothers me as a physicist. It's not just that we haven't gone back. It's that we seem to have lost the capability. We've regressed. We took this giant leap forward and then we took several steps back. And that tells us something important about human civilization, about progress, about our future in space. Let me give you the official explanation first. Money. After Apollo 11, public interest waned. The Vietnam War was draining resources. The economy was struggling. NASA's budget was cut drastically. By the mid-1970s, the Apollo program was cancelled. We'd planned missions through Apollo 20, but we stopped at Apollo 17. And you know what? That explanation makes sense. The moon landings were expensive. The entire Apollo program cost over $25 billion in 1/962 seconds money. That's over $280 billion in today's dollars when you account for inflation. That's an enormous amount of money. More than the Manhattan Project, more than the Panama Canal. One of the most expensive projects in human history. And what did we get for it? Scientific knowledge, certainly. Technological advances, yes. National prestige, absolutely, but no practical benefit, no lunar colonies, no helium-3 mining, no strategic advantage, just rocks and data and bragging rights. So when the political will evaporated, when the public lost interest, when the budget pressures mounted, the program ended. It makes perfect sense from an economic and political perspective. But here's what troubles me. We didn't just stop going to the moon. We lost the capability to go. The Saturn V production lines were shut down. The tooling was destroyed or lost. The engineers retired. The institutional knowledge disappeared. Within a decade of the last moon landing, we could no longer replicate what we done. Think about that. We achieved something extraordinary, and then we deliberately dismantled our ability to do it again. It's like climbing Mount Everest and then burning all your climbing equipment. Why would you do that? The answer is that we didn't think we'd need it again. We thought the moon was conquered. Done. Mission accomplished. Time to move on to other things. The space shuttle, the space station, maybe Mars someday. But we were wrong, because now, 50 years later, we want to go back to the moon. And we're having to start almost from scratch. We're designing new rockets, new spacecraft, new systems. We can't just pull the old Saturn V blueprints off the shelf and build new ones. We have to reinvent everything. And that's incredibly frustrating because it means we wasted 50 years. We could have been building on Apollo, advancing our capabilities, establishing a permanent presence on the moon. Instead, we abandoned it and fell backwards. Now, some people say we didn't really go to the moon in the first place, that it was all fake to win the Cold War propaganda battle against the Soviets. And in part 1 and part 2, we looked at why that theory doesn't hold up. The evidence is overwhelming that we really went. But here's an interesting question. Even if we really went, even if the landings were genuine, could they still have been partly propaganda? Could the real reason we went and the real reason we stopped be political rather than scientific? And the answer is yes, absolutely. The moon race was fundamentally political. Kennedy didn't say we're going to the moon for science. He said we're going to the moon to beat the Soviets, to demonstrate American superiority, to win the space race. And once we won, once the Soviets gave up trying to match us, the motivation evaporated. We'd achieved the political goal. Why keep spending billions of dollars? This is the reality of space exploration. It's not driven by scientific curiosity alone. It's driven by politics, by economics, by national prestige. And when those drivers disappear, the programs end. Now, let me talk about what's happened in the 50 years since Apollo. We built the space shuttle. It flew 135 missions over 30 years. It was reusable, which was supposed to make space access cheaper. But it didn't. Each shuttle flight costs about $500 million. More expensive than an Apollo mission when you account for all the refurbishment and support costs. And the shuttle couldn't go to the moon. It could only reach low Earth orbit a few hundred miles up. The moon is 240,000 miles away. The shuttle had maybe 1% of the capability needed to reach the moon. So we traded the ability to go to the moon for the ability to go to low Earth orbit repeatedly. Was that a good trade? Depends on your goals. If you want to build a space station, yes. If you want to explore deep space, no. Then we built the International Space Station, an incredible achievement, a permanently crewed outpost in space. But again, it's in low Earth orbit, not the moon, not Mars, just 250 miles up, barely scratching the edge of space. And we've learned a lot from the ISS about long-duration space flight, about living in microgravity, about international cooperation. All valuable, but we haven't expanded beyond low Earth orbit. We've been circling the Earth for 50 years while the moon sits there, untouched 250,000 miles away. Now things are changing. NASA's Artemis program plans to return humans to the moon. Maybe in 2026, maybe later. It keeps getting delayed and it's expensive. Really expensive. The Space Launch System rocket that will carry astronauts to the moon costs over $2 billion per launch. $2 billion for a single launch. Compare that to Apollo. The Saturn V cost about $185 million per launch in 1960 seconds. That's about $1.3 billion in today's money. So, the new rocket is actually more expensive than the old one, even accounting for inflation. Why? Because we're not just recreating Apollo. We're trying to build something better, something more capable, something safer, and all of that costs money. But here's what really gets me. Private companies are doing it cheaper. SpaceX is developing the Starship rocket. When it's operational, it should cost maybe 100 million per launch, maybe less. That's 20 times cheaper than NASA's space launch system. How is that possible? How can a private company do it so much cheaper than NASA? Well, several reasons. SpaceX is reusing rockets. They land the boosters and fly them again. NASA isn't doing that with SLS. SpaceX is using modern manufacturing techniques, 3D printing, computer control machining, vertical integration, and SpaceX has a different culture. They move fast, they fail, they learn, they iterate. NASA can't do that anymore. They're bound by politics, by bureaucracy, by contractors spread across every congressional district. Every decision is a political decision. Every component is built in a specific state to satisfy a specific senator. So NASA has become less efficient, less innovative, less capable than they were in the 9 on 60 seconds. Not because the engineers are worse, the engineers are great, but because the system has IFI'd. It's become sclerotic. And that's frustrating because it means we're not living up to our potential. We achieved incredible things in the 9 and 60 seconds. And now, with vastly better technology, we're moving slower. But here's the good news. Private space companies are changing the game. SpaceX, Blue Origin, others, they're innovating. They're reducing costs. They're making space access routine. And this might be what finally gets us back to the moon. Not government programs, but commercial interest, tourism, mining, research. If there's money to be made on the moon, companies will find a way to get there. Now, let me talk about something that really demonstrates how we've changed: risk tolerance. In the 9 on 60 seconds, we accepted enormous risks. The astronauts knew they might die. Some did die. The Apollo 1 fire killed 3 astronauts, but the program continued. We accepted the losses and pushed forward. Today, we can't do that. After the Challenger disaster in 1986, the shuttle program was grounded for 3 years. After the Columbia disaster in 2003, it was grounded for 2 years. Every failure triggers massive investigations, safety reviews, redesigns, and that's good in many ways. We should value human life. We should minimize risks. But it also makes bold exploration much harder because exploration is inherently risky. There's no way to eliminate all danger. The astronauts of the 962 seconds understood this. They were test pilots. They were used to risk. They accepted it as part of the job, and that mindset allowed rapid progress. Today's astronauts are still brave, but the institutions around them are risk-averse. Every mission has to be as safe as possible. Every contingency has to be planned for, and that's expensive and time-consuming. So, we've traded speed for safety. And again, that's not necessarily bad, but it does explain why progress has been slower. Now, let me talk about something else that's changed: public interest. In the 960 seconds, the entire nation was focused on the moon race. People watched the launches on TV. Children dreamed of becoming astronauts. It was part of the national identity. Today, space exploration doesn't capture the public imagination the way it used to. Yes, there are enthusiasts. Yes, SpaceX launches get some attention, but it's not the same. It's not a national obsession. Why? Well, partly because we've already done it. The moon landing was historic because it was first. Going back won't have the same impact. It's been done before. And partly because we have other concerns: climate change, political division, economic inequality, pandemics. Space exploration seems less urgent when we have problems here on Earth. But I think that's short-sighted because space exploration isn't just about exploring space. It's about advancing technology. It's about inspiring the next generation. It's about ensuring humanity's long-term survival. You see, Earth is fragile. Asteroids could hit us. Supervolcanoes could erupt. Climate change could make the planet less habitable. Pandemics could devastate the population. We're all on one planet, one tiny blue dot in an enormous universe. And if something catastrophic happens, if Earth becomes uninhabitable, We need somewhere else to go. The moon could be a stepping stone. Mars could be a backup. Space colonies could ensure humanity survives even if Earth doesn't. That's the real reason to explore space. Not for rocks or flags or national pride, but for survival, for the long-term future of our species. Now, let me talk about the physics of why space is so hard. Why we can't just easily go to the moon or Mars whenever we want. It all comes down to energy, specifically the rocket equation. To escape Earth's gravity, you need to reach about 11 kilometers per second. That's 25,000 miles per hour. And to achieve that speed, you need enormous amounts of energy. And that energy comes from chemical rockets burning fuel. But here's the problem. Fuel has mass. And to lift that mass, you need more fuel. And that fuel has mass too. It's exponential. For every kilogram you want to send to the moon, you need dozens of kilograms of fuel. That's why the Saturn V was so huge. 3,000 tons at launch, but only 45 tons of payload to the moon. The rest was fuel and structure, a ratio of about 67:1. And we're still using the same basic technology, chemical rockets. We haven't fundamentally changed how we get to space since the 960 seconds. We've improved the efficiency a bit. We've made rockets reusable, but the basic physics is the same. To really transform space travel, we need new propulsion technologies. Nuclear rockets, for example, they could be much more efficient than chemical rockets. You could get the same thrust with much less fuel. But nuclear rockets are politically difficult. People don't like the idea of launching nuclear materials into space. What if the rocket explodes? What if radiation leaks? The risks seem too high. So, we're stuck with chemical rockets for now. And that limits what we can do. It makes space travel expensive and difficult. In the long term, and I'm talking centuries here, we need to move beyond rockets entirely. Maybe space elevators, maybe launch loops, maybe electromagnetic catapults, technologies that don't require carrying all your fuel with you. But we're not there yet, not even close. So, for now, we're stuck with the rocket equation. And that's one fundamental reason why space is hard. Now, let me talk about Mars because that's really the next frontier. The moon is close. We've been there. Mars is the challenge. Mars is where we need to go next, but Mars is incredibly difficult. It's 140 million miles away at its closest. The trip takes 6 to 9 months. The astronauts would be exposed to radiation the entire way. They'd experience muscle and bone loss from microgravity. They'd face psychological challenges from isolation. And when they get to Mars, they'd have to land on a planet with a thin atmosphere, too thin to use parachutes effectively, but thick enough to cause heating during entry. They'd have to survive on a cold, dry, toxic world with no breathable air, no liquid water, and intense radiation. And then after doing all that, they'd have to take off again and make the 6 to 9 month journey home. It's incredibly challenging, far harder than the moon. Some people say we should skip Mars and go straight to building space stations or colonies. O'Neill cylinders, rotating habitats in space. These would provide artificial gravity, protection from radiation, controlled environments. And you know what? That might be easier than Mars in some ways. You can build a space habitat anywhere. You don't need a planet. You just need raw materials from asteroids and energy from the Sunday. But psychologically, people want to go to planets. We're evolved for planetary life. We want ground beneath our feet, a horizon, a sky, even if it's a Martian sky. So, I think we'll pursue both space stations and planetary colonies. Different approaches to the same goal, expanding human civilization beyond Earth. Now, let me talk about timelines. When will we actually go to Mars? NASA says the 2030s. Maybe if the funding holds, if the technology works, if the political will persists. SpaceX is more ambitious. Elon Musk talks about the 2020s, building a city on Mars, sending hundreds of people. But that seems optimistic, wildly optimistic. My guess? First humans on Mars in the 2032s, a small crew, A short stay, a flags and footprints mission like Apollo, and then decades more before we establish a permanent presence. It's going to be slow, much slower than people hope, because Mars is really hard and because we don't have the same urgency we had with the moon race. Unless something changes, unless China or another country makes it a national priority, unless there's a new space race, then things could accelerate. Competition drives progress. That's what got us to the moon. Kennedy framed it as a race against the Soviets. And that motivated the spending, the effort, the focus. Maybe we need that again. A new competitor, a new challenge, something to drive us forward. Now, let me talk about something philosophical. The meaning of space exploration. Why does it matter? Why should we care? Some people say we shouldn't. They say we should fix problems on Earth first. Poverty, disease, climate change. Spend money on those, not on space. And I understand that argument. I really do. There are serious problems on Earth that need attention. But here's the thing. Space exploration doesn't take away from solving Earth's problems. The entire global space industry is about 400 billion per year. That sounds like a lot, but it's less than 0.5% of global GDP. It's a tiny fraction of what we spend on everything else. And space technology helps solve Earth problems. Weather satellites help predict storms and save lives. GPS enables navigation and commerce. Earth observation satellites monitor climate change, deforestation, ocean health. Communication satellites connect remote areas. The technology we develop for space, solar panels, water purification, medical devices finds applications on Earth. Space exploration drives innovation that benefits everyone. But more than that, space exploration is about hope. It's about believing in the future. It's about dreaming big. It's about showing what humans can accomplish when we work together toward a common goal. The Apollo program inspired an entire generation. Kids who watched the moon landings became scientists, engineers, entrepreneurs. They created the technologies we use today. Computers, the internet, smartphones, all of it traces back in part to the inspiration and innovation of the space age. So space exploration isn't a luxury. It's an investment in our future. It's how we inspire the next generation to solve the challenges we face. Now let me talk about something that really excites me. The Kardashev scale. I've mentioned this before, but let me go deeper. This is a way of classifying civilizations based on energy use. Type 1 is planetary. We control all the energy of our planet. We can manipulate weather, prevent earthquakes, harness geothermal energy, solar energy, everything. We're currently about type 0.7. We're getting there, but we're not there yet. Type 2 is stellar. We can harness all the energy of our star. A Dyson sphere, a megastructure that surrounds the sun and captures all its output. Sounds like science fiction, but it's physically possible. Type 3 is galactic. We can harness the energy of an entire galaxy. We're talking about a civilization that spans millions of star systems, that can manipulate black holes, that operates on a cosmic scale. Now, where are we? We're type 0.7. We still get most of our energy from fossil fuels, dead plants. That's primitive. That's caveman stuff on a cosmic scale. But we're transitioning. Solar power, wind power, nuclear power, clean energy. In 100 years, maybe 200, we'll hit type 1. We'll be a planetary civilization. And then the next step is type 2. To reach that, we need to expand into space. We need to colonize other worlds. We need to build solar power satellites, space habitats, maybe eventually a Dyson sphere that's thousands of years away, maybe tens of thousands, but it's the direction we're headed if we don't destroy ourselves first. And that's the key question. Will we make it? Will we survive long enough to become a type 1, type 2, type 3 civilization? Or will we destroy ourselves through war, environmental collapse, or some other catastrophe? I'm optimistic. I think we'll make it, but it's not guaranteed. We have to work for it. We have to make the right choices. And space exploration is part of that. It's how we ensure long-term survival. It's how we spread humanity across multiple worlds so that no single disaster can wipe us out. Now let me talk about something personal. My own journey with physics in space. When I was 8 years old and I saw that photo of Einstein's unfinished manuscript, I knew I wanted to understand the universe. I wanted to know how everything works. And as I learned more, as I studied physics, I realized that space is part of that. Understanding the universe means understanding not just the laws of physics, but also our place in the cosmos. The moon landings showed us something profound. They showed us Earth from space. That famous Earthrise photo from Apollo 8, the blue marble photo from Apollo 17, these images changed how we see ourselves. We realized that Earth is small, fragile, a tiny island of life in a vast, hostile universe. And that realization led to the environmental movement, to the understanding that we need to take care of our planet because it's the only one we have. But it also showed us that we don't have to stay on this one planet forever. We can reach other worlds. We can expand our horizons. We're not limited to Earth, and that's a powerful idea. It means the future is open. It means we have choices. It means humanity has a destiny beyond this one planet. Now, let me address something important. The conspiracy theories. Why do people believe the moon landings were faked? Part of it is distrust of government. People saw the government lie about Vietnam, Watergate, all kinds of things. So, they think if they lied about that, maybe they lied about the moon, too. Part of it is the seeming impossibility of it. As we've discussed, the moon landings really were incredible, almost too incredible to believe. So some people just can't accept that we actually did it. And part of it is the desire to be part of a special group that knows the real truth. Conspiracy theories make people feel smart, like they figured out something others haven't. But the evidence is overwhelming. We really went to the moon. The physics works out. The engineering makes sense. The independent verification confirms it. The physical evidence exists. Believing it was faked requires you to believe in an enormous conspiracy involving hundreds of thousands of people over 50 years with no credible leaks. That's far less plausible than believing we actually went. So when people ask me, do you really think we went to the moon? I say, yes, absolutely, without question. The evidence is clear. But I also understand why it seems impossible, because it really was almost impossible. We achieved something extraordinary, something that pushed the limits of human capability. And maybe that's the real lesson. Not that we can easily go to the moon anytime we want, but that we can do incredibly difficult things when we're motivated, when we focus our resources, when we have a clear goal. Now, let me talk about the future. What comes next? Where do we go from here? First, we need to return to the moon, Artemis, or some other program. We need to establish a permanent presence, a lunar base, a stepping stone for deeper space exploration. Then Mars, probably in the 2030s or 2042. First missions will be short exploratory, but eventually we'll establish a permanent settlement. And then what? The asteroid belt, the moons of Jupiter and Saturn. These are rich in resources. Water, ice, metals, organic compounds, everything we need to build more spacecraft, more habitats, more infrastructure. Over centuries, we'll spread throughout the solar system and eventually beyond to other star systems, to other planets orbiting other stars. That's the long-term vision. That's where we're headed. Not in my lifetime, probably not in your lifetime, but in the lifetime of our descendants. And it all starts with those first steps. The moon, Mars, building the capability to live and work in space. Now, people ask me about the Fermi paradox. If the universe is so vast, where are all the aliens? Why haven't we seen evidence of other civilizations? And there are many possible answers. Maybe intelligent life is rare. Maybe civilizations tend to destroy themselves before they can expand. Maybe they're out there, but we haven't noticed them yet. Or maybe, and this is what worries me, maybe space is even harder than we think. Maybe most civilizations never make it off their home planet. Maybe they get stuck like we've been stuck for the last 50 years. And if that's true, then it's crucial that we don't give up, that we keep pushing, that we overcome the challenges and become a true space-faring civilization. Because the alternative is to stay on Earth forever, and eventually something will happen to Earth. An asteroid, a supervolcano. The sun will die on long enough time scales. Extinction is inevitable if we stay on one planet. So we have to expand. We have to become a multi-planet species. Not for adventure, not for glory, but for survival. Now let me talk about my parents. They were immigrants. They came to America with nothing. They worked hard. They believed in the American dream. And part of that dream was the space program. My father would watch the moon landings on our little black and white TV. And even though he didn't understand the science, he understood what it meant. It meant that anything was possible, that humans could achieve incredible things. And that inspired me. It made me want to be part of that, to contribute to human knowledge, to help push the boundaries of what's possible. And that's what space exploration is really about. It's about inspiration. It's about showing what we can accomplish. It's about believing in a better future. When I teach students, I tell them this. Don't just memorize facts. Understand principles. Ask big questions. Dream big dreams. Because the universe is vast and wonderful and full of mysteries. And we have the privilege, the incredible privilege of being able to explore it, to understand it, to expand into it. The moon landings were just the beginning, a first step. We stumbled after that. We lost our way for a while, but we're finding it again. And in the coming decades, we'll go back to the moon. We'll go to Mars. We'll build the infrastructure for a true space civilization. It won't be easy. It'll be incredibly hard. Maybe even impossible by current standards. But so was the moon landing, and we did that. So we can do this too. We can overcome the challenges. We can solve the problems. We can achieve the impossible because that's what humans do. We dream. We explore. We push boundaries. We reach for the stars. And one day, maybe not in my lifetime, but someday, humans will stand on worlds light years from Earth. We'll look up at an alien sky. We'll see unfamiliar constellations. And we'll know that we made it. That we became a true space-faring species. That's the dream. That's the vision. That's why the moon landings matter. Not because we planted a flag 50 years ago, but because they showed us what's possible. They prove that space is hard, but not impossible, difficult, but achievable. And now it's up to us, to this generation and the next, to build on that legacy, to not let another 50 years pass without progress, to keep pushing forward, because the universe is waiting. The future is calling, and humanity's destiny is among the stars. So, when people ask me, was it impossible for humans to land on the moon, I tell them this: yes, it was impossible. By any reasonable measure, it should have been impossible, but we did it anyway. We achieved the impossible, and that's the most human thing of all.